Alright, in this video we're going to look at a special set of numbers called the Catalan numbers. And to start, let's pose a problem, a little example here. So in here, on a graph, I'm going to start at 0, 0 and end at 5, 5. And I'm not allowed to, I'm only allowed to make two types of move, either one move right or one move up. I want to know in how many ways I can go from 0, 0 to 5, 5 without passing above y equals x. I can land on y equals x, actually start on y equals x and end on y equals x. But I never want to have my y value greater than my x value. And we know if I don't have this restriction, I have two types of moves, either right or up. And I need to have right 5 times and up 5 times, and that's going to get me to 5, 5. If I didn't have this restriction here about never passing above y equals x, then I know that that's going to just be measured in 10 choose 5 ways. Because I have 10 things, I can choose any one of those 5 to be right or up. But a lot of those, and it's not going to be exactly half, that might be what you might think. It's not going to be exactly half. A lot of them will actually pass above that y equals x line. So this isn't going to be my complete answer. I'm going to actually use this in the answer, but you can see, so just as an example, I can go right, up, right, up, right, up. I think I need to go, right, up. And that's one acceptable path, where notice I have not passed above the line. But if I go right, up, up, I've broken the rule. I've passed above the line. So before we go to a straight formula for this, let's make sure we understand what's going on. So an example of a good path. I cannot start by going up, because then I'd be above the line. But I can start by moving right. I actually have to start moving right. And at this point I can either go up or right. I'll go right again. At this point I can go up or right. Let me go up. I can go up or right here. I'll go right again. I can go up or right here. I'll go up. No, so I'm just selecting these moves somewhat at random. I can go up or right. I'll go up again. I can go up or right. I'll go right. I can go up or right. I'll go up, and notice I've gone from 0, 0 up to 4, 4 so far. I need to get up to 5, 5. At this point, I only have one choice. I cannot go up because I passed the line. I think I might have said I could go up here. I can't go up here. I have to go right. Same thing here. I have to go right. And I now have to go up because if I go right, I can't make a step left and get back. So that's one example of a good path. Whereas an example of a bad path might be going right, going up, going right, going up, and going up again. Anything after this is already a bad path. It doesn't matter if I go directly back over to go under, or if I go up even further. I've passed above this line, so that's a bad path. Now, for these paths, I can represent them by the moves right and up. So this path here went right, right, up, right, up, up, right, up, right, up. Notice we have 5 rights and 5 ups, just like we talked about in the 10 choose 5, but I have to make sure that I don't go up too far. And we'll talk about what that means shortly. In this one, I have right, up, up. I'm going to put an arrow here. This is important. This is where we first broke the crossing rule. Then we went up again, then 2 times right, and up, and a right again. And you can still see there's still 5 R's and 5 U's, but this is a bad path. We gotta somehow count this. And so in here, why is this a bad path and why is this a good path? Well, The problem is this. I need to stay below the line, which means I need to have the number of r's greater than or equal to the number of u's at each step along the way. So at this point in here, I have 1 r. I have 2 r's. 2 r's and 1 u. See, r is still bigger than u. 3 r's and 1 u. 3 r's and 2 u's. 3 r's and 3 u's. They can be equal to. 4 r's and 3 u's. 4 r's and 4 u's. So this one, the number of u's never exceeds the number of r's. Number of ups never exceeds the number of rights. But in here, I start off with 1 r. That's okay. 1 r and 1 up. That's okay. 2 r's and 1 u. That's okay. 2 r's and 2 u's. That's okay. But right here, 2 r's, 3 u's, this is where things go badly because I've gone too far up. Now it doesn't matter what happens afterwards. There's no fixing it. So let's look and see what's happening here. So an example of a good path, so I'll make a good path green, I could do right, up, right, right, up, right, up, up, right, up. And I'll write all that stuff down. So right, up, right, right, up, right, up, up, right, up. And if we dive right in, we can try to say, okay, I know it has to start with an R because I can't start with a U. So that eliminates some possibilities. I know it has to end with a U because if I ended with a right, I'd be coming at it from this side. But as you get more and more values, this quickly falls apart. Even up to here, I may be able to reason, okay, there's only one choice for the first. After that one choice, there are 2 choices. So I could try to make a tree. There's one choice for the first. Then I can either go right or up. So there's only right there. If I go right, then I'm over here. I have 2 choices. I can still go right and up. If I go up, I only have 1 choice. And I could probably get through the tree diagram for this. It's not too large, but imagine trying to consider all of these possibilities for going from 0, 0 to 100, 100. So instead of trying to do this directly by measuring the number of ways to get from here to here, let's look at what breaks things. And so let's consider these. I'll put these up here in red because these will be bad paths. And so let's consider right, up, up, right, right, up, right, right, up, up. Okay, and I guess I'll write it to the side. I'm going to need some more room. So we had right, up, up, right, right, up, right, right, up, up. Still 5 and 5 for R's and U's. But what we can do is this. This is where the trick comes in. The first bad move is this right here, this first up. The second up, because it's 2 ups after just 1 right. And so what we can do is actually change this. I'm going to change the direction of each of these. So instead of R, I'll put U. Instead of U, I'll put R. And I'll keep these 3 the same, so R, U, U. And what actually happens now is if I follow this path, so I go right, up, up, and then instead of going right, I go up, up, right, up, up, right, right. I don't get to 5, 5 anymore. I get to 4, 6. There are now, so in this case, there are now only 4 R's and 6 U's. well, let's see, is that a coincidence if I follow the same process? Let's try another example. So in this one, I'll start off by going right, right, up, right, up, 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 right, right. So I write that down, W-R-I-T-E, R, R, U, R, U, 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 R, R. And the first U that breaks this, so it is this one right here. This one right here. So I will cut this afterwards, change those from URR to RUU. I'll keep everything else the same. R, R, U, R, U, U, U. And when I do that, so I go right, up, up from this point, I end up at 4, 6 again, which means that I have 4 R's and 6 U's. And this isn't a coincidence. So if you think this through, if I break this, so the breaking point is when there is one more U than, not tan, than R. Okay, so once I get one more U than R, that's the breaking point. And if I go ahead then, and so if I switch the remaining, what's going to happen is I will have 2 more U's than R's, because at the start I have 5 R's, 5 U's. This one broke here at the point where I had 3 R's, 4 U's. And here I still end up with 5 R's and 5 U's then, so this has 2 R's and 1 U. But if I flip it around, now this still has that 1 extra U. And this, which had an extra R to compensate for the extra U here, when I switch them, now has another extra U. So I have 1 R and 2 U's. And you can see, this doesn't matter where the break happened. So I go back to the previous slide. When it happened here, I had 1 R and 2 U's. And then I had, to make up for that, 4 R's and 3 U's, which I changed to 4 U's and 3 R's. So it doesn't matter where it gets broken. When I switch the rest, I end up having 2 extra U's. And so this is where it all gets sort of wrapped up, is the total number of ways to go from 0, 0 to 5, 5 is 10, choose 5. I have 10 moves, I choose 5 of them to be U's or 5 of them to be R's. It doesn't matter which way you think about this. But every breakable, or every broken path, you can have a one-to-one correspondence to a path that has only 4 R's and 6 U's. Or you can think of it differently, 6 U's and 4 R's. So this is the way I can find this answer, and when I work that through, that's going to be 42. And that's really worth considering. So there's this 1-to-1 correspondence between bad paths, and that should make sense. When I flip that thing, I'll get the 2 extra U's to the 4 R's and 6 U's. The harder thing to probably visualize is the fact that the 4 R's and 6 U's has a one-to-one correspondence back to a bad path, but we can go there. So let me just put up a random string of numbers that have 4 R's and 6 U's. And I'll do this in this purple. So R, U, U, R, R, U, 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 R, U. Okay, 4 R's, 6 U's. I can actually undo the sort of transformation the exact same way. The function is its own inverse here. Take the first element, find the element that breaks it, R, U, U. This breaks it. I have too many U's. And switch the rest. And when I do that, whenever I take one of these 6U, 4R's, I can rewrite it into a string that is bad, does not count for the Catalan numbers. So that's what I do here, and that leads me straight to this. So definition and a formula. So the Catalan number b sub n measures the number of ways to get or go from 0, 0 to n without going above y equals x. And of course, I'm not going to write it. I have enough writing here, but I mean that we're only going to this lattice point. We're only making one step right, one step up. The formula for this is the following. So b sub n will equal 2n choose n minus 2n choose n minus 1. And you think this through. In the previous example, n was 5. I take 10 steps, n is 5. So I have 10 choose 5, 10 steps, 5 of them being right. And then I take away that thing that was a one-to-one correspondence with all of the bad paths. Okay, so one example here. Calculate B3 and represent each of the possible paths on a grid. So B3, alright, B3 is just going to equal 2n, 6, choose n, 3, minus 2n, 6, choose 3 minus 1, 2. And I can do the calculator. For the larger numbers, I will use a calculator. I'll do this one by hand. So 6 choose 3 is 6 factorial over 3 factorial, 3 factorial. 6 choose 2 is 6 factorial over 6 minus 2, 4 factorial times 2 factorial. In here, I can cancel some stuff out, so I'm going to look at these. 6 is 3 bigger than 3, so I get 6 times 5 times 4 times this 3 factorial, which will cancel out with this 3 factorial, and then I have a 3, 2, 1, so those cancel. Minus, this 6 and this 4 are going to reduce down. 6 is 2 bigger than 4, so I have 6 times 5, and then I get the 4 factorial, because 6 times 5 times 4 times 3 times 2 times 1. This 4 factorial is going to cancel out, times 2 times 1. In here, 3 times 2 times 1 is 6, so let me change some colors. This 6 will cancel out with those, and I'm left with 5 times 4 here, which is 20. In this, they don't fully cancel, but the 6 over the 2 gives me 3. 3 times 5 is 15, so I get 20 minus 15, which is 5. So there are 5 possible paths. And now, let's try to represent them on these grids. So the simplest path to probably start is just going all rights, 1, 2, 3 rights, and then all ups, 1, 2, 3 ups. And for something this small, it's actually not too hard. I can go 2 right, 1 up, 1 right, 2 up. I can go 2 right, 2 up, 1 right, 1 up. I can go right, up, right, right, up, up. And then finally, right, up, right, up, right, up. 5. And if you try to do any more, you won't be able to find any more. These are the only 5 ways that I can make these steps and not go above y equals x. And one more example now. In how many ways can you arrange the numbers 1, 2, 3, 4, 5, 6 so that when reading from left to right, you will at no time have read more even numbers than odd numbers? And the applications of the Catalan problems, a lot of them have to do with making sure that you never pass something up. So in this case, we have odd, even, odd, even, odd, even. And if I just have this set of elements, there will be 3 ways to arrange this so that, let's see, no time anymore, so that you'll always have more O's before you get E's. And we just saw B3 is 3 times 2, 6, choose 3, minus 6, choose 3 minus 1, 2. And we just calculated that that's going to be 5. But in this problem, there's one more issue. All of the odds are not the same. They're distinct. We have a 1, we have a 3, we have a 5. All the evens are not the same. They are distinct. And so I take this B3, and I need to multiply by the number of ways to arrange the 3 odd numbers, 3 factorial, and the number of ways to arrange the 3 even numbers, 3 factorial. Because if I have, let's say this is an all right arrangement because I will always have at least as many odd numbers as I have even numbers. But this odd number could be a 1 or a 3 or a 5. This could be one of the remaining 2 odds. So this is the correct way to do it. That's going to be 5 times 3 factorial is 6, 3 factorial is 6, and I will get, let's see, 5 times 6 is 30, times 6 is 180. Okay, I will put up another video with some more examples of Catalan number problems. Comment if you've got any questions.